Here comes the sky.
Alright, so give 3 equations that express the total energy of an object experiencing simple harmonic motion. The first one, our total energy, 1/2 Ka squared. When do we use this equation? We use this at the endpoints. That means all of our energy is at an endpoint. If you recognize something is probably simple harmonic motion, then treat it, for me, I treat it like a pendulum. I know that at my endpoint, all of my energy is based on my maximum displacement from my point of equilibrium. Right? Maybe it's better for you to imagine it as an oscillating mass on a spring. And when you're at an endpoint, that'd be our EQ. This would be the endpoint. All of our energy is stored within the spring. So it would normally be 1/2 kx squared, but in this case it's 1/2 ka squared. So at endpoints, let's go ahead and just name this as springs. So this is our spring endpoints total energy. The total energy for equilibrium would be 1/2 mv squared. And that v would specifically be the maximum velocity. And that happens at the equilibrium point for a pendulum or for the spring. So either one. You can get your total energy. All of your energy is just kinetic energy. And then finally we have total energy somewhere in between. So all the points. And that's going to be 1/2 mv max squared plus 1/2 ka or kx squared, because it's not exactly our amplitude. It could be any section along this path. So there you go. Show how the equation for maximum speed of an oscillating object is derived from the conservation of energy. Conservation of energy tells us the total energy in the beginning has to equal the total energy in the end. So to solve this, or to show this, we're going to get Vmax all alone. And we're going to keep it in terms of the spring constant, mass, and amplitude. So TMEI equals TMEF. What do you want to do? Spring? Pendulum? I prefer the pendulum, so let's go ahead with the pendulum. My total mechanical energy in the beginning, so let's say I have my gravitational potential energy in the beginning. And then my energy at the equilibrium will be my end point, and I know that's going to be my kinetic energy, my maximum kinetic energy. So this becomes mgh equals 1/2 mv max squared. Okay. Mass on both sides, multiply by 2, and take the square root, and we get Vmax equals the square root of 2gh. Okay, that's not up there. That's not one of those equations we just derived. So we're going to have to look at it like a spring. So with a spring, if we are way up here and then our equilibrium is way down here, TMEI equals TMEF. In the beginning, we have spring potential energy equals maximum kinetic energy. So 1/2 Ka squared equals 1/2 mv squared. Multiply by 2 on both sides, our fraction goes away. We don't have mass on both sides, so we can't just cancel out mass. Instead, we're going to divide by mass on each side, and we get v squared equals Ka squared over m. And when you take the square root of that, you get v equals a times square root k over m. Square root k over m. Think back. That was something, wasn't it? We showed earlier, in an earlier video, how that was omega. So our amplitude times omega equals Vmax. Then we also have seen this someplace. How does the equation for maximum speed of an oscillating object, that thing, relate to the speed of a moving object in circular motion, uniform circular motion? So we have uniform circular motion here. Uniform circular motion, we've got maximum speed would be v equals omega times r. R is the radius of a circle. Simple harmonic motion, we have Vmax equals A times omega, and A is our amplitude. So there's your direct relationship. Show how the equation for maximum acceleration of an oscillating object is derived from Newton's second law. Newton's second law tells us the stuff that makes it go minus the stuff that holds it back equals mass times acceleration. So let's go ahead and do this. Oscillating object. Let's use Newton's second law. Pendulum could be gravity. Spring, stuff that makes it go, could be the spring force. Let's go ahead and use a spring for this one. Okay, so the stuff that makes it go when it's oscillating up and down. When it goes down, it's being pushed. When it goes up, it's being pulled by the spring. So the stuff making it go is going to be our spring force minus the stuff that holds it back. Nothing, right? Can't be anything because we're in simple harmonic motion. So that equals mass times acceleration. Our spring force, if you remember, is k times x. X is our displacement. K is our spring constant. So we have k times x equals ma. X is a good variable to use whenever we're at these in-between points, but if we're at a maximum spot, we call that amplitude, right? Amplitude. So when our amplitude is greatest, what happens to our acceleration? It is also the greatest. So our acceleration is now a max. And when we solve for a max, we get k times a over m. K over m. Is that anything? K over m. Angular velocity, right? We've shown that. Well, it's not really angular velocity. We got to do a little something to it. It would be the square root of k over m would be our angular velocity. So if it doesn't have that square root thing, then it must have been squared, right? So this equals omega. Well, k over m, if I square both sides, that gets rid of the square root. That must mean that equals omega squared. So our equation becomes a max equals a times omega squared. What do you think about that? That is a process of deriving. First we start off with this, and we made a connection here. Did we make a connection? Let's see. For uniform circular motion, centripetal acceleration is v squared over r. V also equals omega times r, so if it's v squared, it's omega squared times r squared. Cancel those out. AC equals omega squared times r.